take the second derivative. Okay, what's the derivative of C1? 0. Here, 2C2, and that's it, right? Plus, okay, this one. 3C3 comes for the ride, 2 has to come down. So 6, right? I'm not going to write it as 6, though, intentionally. I'm going to write it as 2 times 3, C sub 3, x minus a what? To the 1, right? What's the next one? 3 times 4, which is 12. I understand that, but I'm not going to write that. X minus a squared. Plus, next one, 4 times 5 times c sub 5 x minus a to the third plus dot, 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 dot.
Is that where factorials come from?
Well, it's not where they come from, but you can see that they're being generated. It's actually that these patterns appear, and we had to come up with a notation to account for them. So the factorial notation accounts for the fact that they appear. All right. So how do I figure out what c sub 2 is? I'm going to do it on the side here for a second. What's f double prime of a? So it kills everything off except that. So 2c sub 2. So solve for c sub 2, and you get f double prime of a over 2 equals c sub 2. Yes? I think we need to go at least one more time. Let's take the third derivative. Maybe we'll go twice. Third derivative. No, sorry. Third derivative. So derivative of that is 0. Now look what happens here. This is all a constant. Derivative of that's 1. So we get 2 times 3 c sub 3 plus, now check out, I think you're really going to see it now. 2 times 3 times 4 times c sub 4. 2 times 3 times 4 times c sub 4 x minus a to the first power plus, next one, 3 times 4 times 5 c sub 5 x minus a squared plus dot dot dot. So how do I figure out what c sub 3 is? I do f triple prime of a is, kills everything off except that, 2 times 3 c sub 3. Solve for c sub 3. I'll continue my list over here. The third derivative at a over 2 times 3 equals c sub 3. What's the next one going to be? Well, let me write the notation down just so we know it. How do you write fourth derivative? Because at some point you want to stop doing those prime marks. You write 4, close. Not that, that's incorrect. No? Parentheses around the 4. Okay? If you put just f4, like that means raise that function to the 4th power. 4 with the parentheses around it means take the 4th derivative. So when I do my 4th derivative, this goes away. What do I have? This right here, right? 2 times 3 times 4 times c sub 4 plus, and then I'm going to have more stuff, right? I'm not going to write any more down. So my 4th derivative at a should be 2 times 3 times 4 times c sub 4. So c sub 4 is the 4th derivative at a divided by 2 times 3 times 4. The 4th derivative at a divided by 2 times 3 times 4 is this. And is that enough for you to believe in the pattern? Okay. Now, I didn't put the 1s out here. 1, 1, you don't need them, right? 1. Anybody have a guess as to what the formula is, the general formula is for c sub n? Therefore, c sub n should be f nth derivative, right, at a over n factorial. Does that work for all the n's? Yes. Because what happens if you try 0? You get the 0th derivative. What does the 0th derivative mean? Don't take the derivative, right? Okay, so that's the original function at a divided by 0 factorial, which is 1. So that's the original function divided by 1. We didn't see it, but there's a divided by 1. Now we plug in 1, take the first derivative at a, divide it by 1 factorial, which is 1. Second one, second derivative at a, divided by 2 factorial. Third one, third derivative at a, divided by 3 factorial. Fourth one, fourth derivative at a, divided by 4 factorial. Isn't that nice? We have a general formula for C sub n.
For every function?
For every function. You've just got to be able to differentiate it. Okay. That's the power of Taylor series, is that it works for pretty much everything that you can differentiate. All right. So, this old formula for f of x, sum n equals 0 to infinity of c sub n x minus a to the n, we now know what that c sub n is. It's a formula. So this now becomes sum n equals 0 to infinity f nth derivative of f at a over n factorial x minus a to the nth power. There it is. That's the big formula for this section right there. This is called the Taylor series about a, or sometimes you'll hear centered at a. That's what a Taylor series is. Now, what is a Maclaurin series? Let me tell you. A Maclaurin series is a Taylor series about the specific number 0. In other words, if somebody asks you for the Taylor series of a function, they must tell you what a is. But if someone asks you for the Maclaurin series of a function, it's implied that a is 0. So the best analogy I can make is, I can draw an infinite number of rectangles, right? But a square is a specific rectangle, isn't it? So a Maclaurin series is a specific Taylor series when a is 0. Otherwise, the Taylor is more general. Make sense? All right, time for you to do your first Taylor series. This is exciting. All right, I'm actually going to do Maclaurin series. We're going to do Maclaurins today. We'll do Taylor next time. Find the Maclaurin series for f of x equals sine x. So what I'm claiming here is that the function sine x from pre-cal can be written as a power series, as an infinite polynomial. And I want us to find what it is. Well, can you differentiate that function? Yes, and to do the Maclaurin series, I need to be able to take derivatives repeatedly. And I actually am looking forward to that because I know sine just keeps on oscillating back and forth between things. So I'm not too intimidated by this. So my goal right now is to try and figure out what those c sub n's look like, right? So I'm just going to start taking derivatives and then plugging in what to those derivatives? 0. Why 0? Because it's a Maclaurin series. So I'm always going to plug 0 into it, right? So I think the way I like to do this, you know what the function is, right? I like to just make a table. So I start out with the 0th derivative of the function, and I do it at x first. So just give me the derivative of this, or the 0th derivative of this function. It's just sine x, right? Now, go ahead and do the Maclaurin part, which means plug 0 into that. And what do you get? You get sine of 0, right? Sine of 0 is 0. Yes? Sine of 0 is 0. Remember, this number is c sub 0, isn't it? Okay. Now, let's do the first derivative, which is cosine x. And then let's take that first derivative and plug 0 into it. And cosine of 0 is 1. And so our constant, c sub 1, is 1. Then I take my second derivative, negative sine x. Because it's Maclaurin, that's not really going to matter, is it? Because when I plug 0 into that, I'm going to get 0. And that's going to be c sub 2. And then third derivative, negative cosine x. Plug in 0, and you get negative 1. That's my c sub 3. What's going to happen now? It's going to go back to 1, right? Or sorry, it's going to go back to 0. I'm going to start the pattern over, right? Now I'm only starting the pattern over because this is sine, right? Don't know why I put 5 there. Don't know why I put x there. So we're back to 0. And then it's going to be 1, 0, negative 1, 0, 1, 0, right? Negative 1, 0. It's going to continue that pattern. All right. Good. Because this pattern is so simple, what I'm going to do now is just start writing out the infinite polynomial. In other words, I'm going to take this general formula we have. Right? C sub 3, x minus a cubed, plus dot, dot, dot. I'm just going to start writing this thing out. You ready? Remember what those were. So sine x is equal to c sub 0, which was 0, plus, shoot, hold on a second. I screwed this up. I'll admit mistakes. These are not your c sub 0, 1, 2, 3. Remember our formula for c sub n? It was the nth derivative at 0 over what? N factorial. What we got here were not the c's. I totally apologize. Just take the c's completely out of there, okay? Because that was wrong. Okay? Here, someone hit me. You want to hit me? You want to hit me? Somebody hit me? Flog me?
Did you use a bad word? Shoot.
I don't think I did cuss. I should cuss for that, but I'm not going to. Do y'all understand what we got there are these pieces? I left out the n factorials. Okay, let's keep going. So c sub 0 would be the first number off our list, right? Over 0 factorial, right? Yes? X to the 0. I'm using the formula. Let me put the formula up here again, even though I wrote it down. I'm using this formula. And instead of doing x minus a to the n, I'm doing x to the n because we're Maclaurin, so a was 0. Yes? Okay, that's the formula. This was more Taylor, but plugging in 0, we get that. Then plug in 1. What was the first number in our list, or second number in our list? Was it 1? Okay, so 1 over 1 factorial x to the first power. Okay. Plus, what was the third number in our list? 0. So 0 over 2 factorial x squared plus negative 1, good, over 3 factorial x cubed. Yeah? Okay, keep going. 0 over 4 factorial x to the 4th plus, it'll be 1. We're going back to 1 now. 1, 5 factorial x to the 5th. I'll do 2 more. 0 over 6 factorial x to the 6th plus negative 1 over 7 factorial x to the 7th plus dot, dot, dot. Yes? A bunch of those are zeros, aren't they? That's gone, that's gone, that's gone, that's gone. So this is just x, right? Yes? Well, you know what? Can you write that in sigma notation? Let me write it down first. We have 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th plus dot, dot, dot. Can you give that to me in sigma notation? What type of series is that? Alternating? Can you take care of the alternating right now? Negative 1 to the, well, where are we starting? 0? Negative 1 to the n should start us out positive. Because if I let n be 0, negative 1 to the 0 is 1. Then n is 1. That would give me a negative. So that should alternate the way I want, right? Positive, negative, positive, negative. Now let's try and pick up a pattern on the x's. Let's look at the x's first. This is x to the 1st, 3rd, 5th, 7th. 1, 3, 5, 7. Can you generate that list for me? 2n minus 1. So I have x to the 2n minus 1. We're using minus 1 because we want to start it at 0. Plus. We want to start it at 0 and get a 1 up there, right? So we've got the alternating part taken care of. We've got the powers on x taken care of. And now I just need these factorials. 1 factorial, 3 factorial, 5 factorial, 7 factorial. Odd numbers again, right? So I just need to create odd numbers. How about this? 1 over 2n plus 1 in parentheses factorial.
How do you know how many to keep doing?
How what?
How do you know how many to keep doing?
What do you mean? How long? How far to go?
Yeah.
Enough for you to be able to get the pattern. That's how far. Yeah, you need to be able to pick up the pattern. Make sense or no? Okay. Now, of course, like these are all numbers, right? This is like 1 over 6, 1 over something, 120 or something like that. Those are all just numbers in front. Yes?